Hey guys, so today we're talking about a new paddle in special relativity. Actually, it's a new because I knew it for a very long time, but recently it's become famous because many channels have talking about it now. It's called the Andromeda paddle. So what does it mean? So imagine we have an alien civilization that's about to destroy the Earth, they will plane. The plane, if the plane goes successful, they will fly the death ray, which will evaporate our entire planet from the Andromeda galaxy. So imagine the Andromeda is 2.5 million light years away. The actual distance actually that's away from the Earth, and you standing here and you see that you can somehow see faster than the light can communicate to you. I mean, it's ridiculous, but let's assume that. So your friend is running toward the Andromeda. Sorry, it means I standing here and my friend is going at the walking speed, very slow on Earth, nothing special. So according to special relativity, simultaneity is relative. Let me talk about this first. So the most known fact about special relativity is the time dilation. So it's measured how your clock is running slower if you move at certain speed. So faster speed means time run more slowly. But notice that it only talk about the rate at which clock ticking. Relativity of simultaneity is not that famous in relativity, but it's measured differently. It measures the separation between clocks. Imagine you have many clocks around you and you run into us. You run in on the route, you will see the clock desynchronized by a very small amount. How does that work? Well, imagine a very simple experiment. You standing at the center and two grenade or two bomb, let's say a two bomb, far away, and if you shine a laser, it will explode immediately. So you're standing at the laser at the center and you hold two laser handheld, and you fire the laser at the same time, and the distance towards the two bomb is the same, but they're standing opposite. It means the beam will travel opposite at each other from the center that you fire. So what happened? They will upslow at the same time because two beams moving opposite direction at the same speed and travel same distance. But imagine someone on the chain. What would they see? Speed of light is constant for both frames. So that means they also see you find both lasers at the same time, but now the laser travel opposite direction at the same speed, but one grenade is coming towards, and one grenade must be running away. Why? Because according to them, the train standing still and the route is moving. The route is moving, so one beam will hit one grenade and make them explode first, and the second beam will make the other explode later. So that's the point. So imagine we remove the laser and the experiment altogether. The effect's still there. It means if we put two clocks on two grenades and we synchronize them, when the person on the chain will see them desynchronized, they will run off. So, but let's recap. I say that both person who's standing on the train and the route always agree on one thing. The person must fire the laser. Imagine the person fire two lasers, an event called A, and two grenade explode, it's called two event B and C. So they disagree on B and C, which one occur first. The one say it's simultaneous, the one say B occur first, for example. But they must agree that event A must happen before B and C. Why? Causality. So, relativity of simultaneity isn't actually a measure of simultaneity. It's very misleading term. It's actually relativity of non-causal connected event. What do I mean? Not simultaneous when or event that happen faster than the light can communicate between them. So it means that happen faster than the speed of causality. That's what matters. They are outside the light current in the Minkowski space-time diagram. It means that the low-range transformation can affect the order of the event by shifting the coordinate when a person is moving. But it doesn't change which event is inside the light current. It can stretch the duration of the event. That's what called time dilation. It stretch them. For example, the event happened only 5 seconds, but the transformation make them happen in 10 seconds, for example, but the order of causality is always the same. So now we back to the paddle. What total few day means? So the relativity of simultaneity equation only depend on both factor or the speed and the separation distance. So even speed is very slow compared to speed of light, like the walking speed. The distance is actually very big, 2.5 million light years. So it does make a difference about a few days. A few days, I will give or take 3 days or 12 days. But why does matter? So the person assumption that the death beam will be fired right now. So here's how the paradox go again. Sorry, I talk about the unrelated thing. So imagine I'm standing still on the ground, and according to me, the death beam will fire on Earth on 3 days later. A friend of me running toward the Andromeda, it means we have Lorentz transformation making the time 3 days forward. And according to him, the death ray must be fire on Earth because it had been 3 days on the Andromeda galaxy. So what happened? The paradox states that, well, if I standing still here and I don't see anything for 3 days later, and he's moving, so it must become his person, so he will be fired by the laser and death. And I will be absolutely fine because it happened 3 days later. Yeah, that is ridiculous, because why? The death beam hit the Earth, and it will evaporate the entire planet, including me and them. That's locality, right? So yes, that's the problem. The problem is that the event was a blame for making a death ray is in the line of causality. They're inside the light current. Because the death ray travel at the speed of light, I assume it travel at the speed of light or slower, it is inside the light current. The vast light current of Minkowski diagram. So when I say that the person running toward the Andromeda was shifting the time, shifting that to 3 days, it must be the order of the event outside the light current. So it's relatively the same time between here and now on Andromeda galaxy. But remember, the Andromeda galaxy was 2.5 million years away from us, light year away from us. So they are so far away is that the order of the event in 3 days doesn't matter, because the separation too large, 2.5 million light year. And that means that the event, in order to hit the Earth, must happen 2.5 million years ago. But it happened inside the light current. So the Lorentz transformation do not make anything to the event, because they are causally connected to each other. The decision of the person, let's say the president there, want to fire laser to the sound that he makes travel at the speed of sound, and radio communication travel at the speed of light, and into the pain process of the soldier, and even he make that's just studying, they make such the decision to fire the death beam already in the relation of causality, and it's inside the past light current. The point is, we can shift the time by Lorentz transformation, but those events must be outside the light current. And since the Andromeda galaxy is very far, and in order to death ray for hitting Earth right now must happen 2.5 million years ago, we cannot change the 3 days, because the Lorentz transformation had the light current is there. The only way to get away from this event is one of the person, my friend or me, had to travel faster than the speed of light to escape the light current. That's the only way. But we know nothing travel at the speed of light. So that is